Let's write the VHDL description for this circuit. We are going to use a combination of behavioral, data flow, and structuring model to represent this counter design. In video 128, we wrote the VHDL code for a D flip-flop with synchronous, active low, clear N and pre-N. We would need that file in our project or in our code. So I'm assuming that we are going to have that available. So we're going to write the VHDL code, library IEEE, use IEEE dot standard logic underscore 1164 dot all entity counter design. That's our top level. Let's write the ports. So if you look at your original design or your original block diagram, your counter has a reset, a clock, and Q, which is 3 bits. That is basically Q2, Q1, and Q0. So that was basically Q2, Q1, and Q0. So I'm going to write clock input, reset input. So in standard logic, a Q output, which is 3 bits long. So standard logic vector, 2 down to 0. End entity. Remember, this code here used behavioral modeling. Next, let's come to the architecture part. So architecture, arch of counter design is so follow this carefully. So I'm going to make signals, which is Q bar, standard logic vector, 2 down to 0. So all I'm doing is I'm making a signal here, a signal here, and a signal here. Also, I would need an additional signal here, which I'll call it as D2 input. So signal D2 underscore input standard logic. Now declare your component, or component FFD is, this was from the video 128. So D clock reset clear N pre N in standard logic, and Q out standard logic, end component. Let's write the main architecture now. Begin. So first I'm going to find the knots of Q2, Q1, and Q0. So I can write Q bar 2, which is nothing but Q2 prime, is knot of Q2. Q bar 1 is knot of Q1, and Q bar 0 is not of Q0. So these are the three signals. And my fourth signal is D2 underscore input. So D2 underscore input is nothing but Q2 prime Q1 Q0, which is this one here. So I can write D2 underscore input is Q bar 2 and Q1 and Q bar 0. So these are data flow equations. Behavior was for making this component or making the D flip-flop component. Data flow for making Q bar 2, Q bar 1, Q bar 0 and D2 input. And now we are going to use structural programming. So flip-flop 0, that's the tag. Call the flip-flop and port map. So if you remember, for the flip-flop, the first input is D, followed by clock, followed by clear N, followed by pre-N, and then finally the Q output. So for flip-flop 0, the first input is D, which is nothing but Q1 bar, that's here. The second input is clear N, which is nothing but, the second input is clock, which is a common clock. The third input is clear N. Clear N is nothing but reset. The fourth input is pre-N, which is set to 1. And the fifth parameter is Q0, which is the output. So I'm going to write Q bar 1, comma clock, comma reset, comma 1, comma Q0. Similarly, for the second flip-flop, call the flip-flop, port map. So let's look at the inputs and the outputs. So for flip-flop 1, Q2 bar is the first input, clock, then clear N is set to 1, then you have pre-N which is set to reset, and then output Q1. So I can write Q bar 2, clock, 1, reset, comma Q of 1. Next, let's go for flip-flop 2. Call the component and port map. You have D2 input, which was the signal here. So that came all the way here, D2 input, clock, clear N, which is basically reset, pre-N, which is 1, and Q2. So I can write D2 underscore input, comma clock, comma reset, comma 1, comma Q of 2. End. So this is structural. So that's it. That's the VHDL code for a counter which can count this sequence here. So we are done with all 6 items. This is the process to make any counter. You can change the sequence, but the process is going to be the same.